Hello.
Hello.
Hi, Ben. And maybe waiting for a few more people. Okay. So, okay, people are joining. We'll start. So today we're going to talk about geometrical optics. Have you both seen the assignment? Not yet. Okay. You did? Not much. Okay. Well, the topic is geometrical optics. So, and the first we focus on the refraction and reflection of light. Okay. So you probably know what reflection and refraction is. You've probably been studying it in year 8 or something, and then again in year 9 or 10. Well, light reflects and refracts. We know this. Okay, I hope we know this. So today we are going to dig in to those topics a little bit more mathematically, a little bit deeper. And one of the things that really fascinates me about light and refraction of light and reflection of light, that in all cases light chooses the shortest, the quickest path, not the shortest, the quickest path. Let me demonstrate. So, for example, if you take a mirror and bounce light off the mirror. So let's say there is an object, I don't know, a polyhedron like this. Okay, so we have an object. And light from that object hits the mirror and enters your eye. So suppose it is not allowed to travel directly into your eye. Let's say there's some sort of barrier here. But light travels, bounces off the mirror, and then hits your eye. So light travels like this. And it travels in such a way that the angle of incidence is equal to the angle of reflection. You all know this. The angle of incidence is equal to the angle of reflection. But it turns out that taking this particular path is quicker than, let's say, taking any other path, like, I don't know, going here and reflecting in like this. the red path would take longer than the black path. So if the angle of incidence is not equal to the angle of reflection, the light will take longer. Imagine a situation. You have a bonfire which has gone out of control. Imagine you have a bonfire which has gone out of control, and you need, so this is you have a bucket of
screen.
Oh, thank you for letting me know. All right, and you see my screen now?
Yep, thank you.
Okay, right, so going back, so thankfully I have the back arrow so I can walk you through. Right, so let's say you have an object. This is the object, and this is your eye, and the light cannot travel directly from the object to your eye, so you can't see it. It's behind a wall, but you can see it in the mirror. And the light reflects off the mirror and enters your eye, and it does it in such a way that the angle of incidence is equal to the angle of reflection. Because if it took any other path, let's say it took the red path, the red path would take longer. Or in other words, if the angle of incidence is not equal to the angle of reflection, the light will take a longer time to travel. So light chooses so basically I is equal to R because it is the shortest path. It is the quickest. So imagine you have, this is you. You have an empty bucket. You have an empty bucket. You have a bonfire. You are celebrating the 5th of November, and it's gone out of control. Bonfire. And it's about, if you leave it, it will light up the trees, and the trees will light up the forest. It's going to be a problem. So you need to put the fire, put away the fire. You need to put water onto the fire. Okay. And this is a river. This is a river. So you need to get some water from the river, and you need to put out the fire. Yes, put out, that's the word. So you can run like this, for example, and then like this, or you can run like this, and then like this. It turns out that the quickest way, well, as long as you, there is an issue here, but we'll talk about the issue later. That if it will be quickest if this angle of incidence is equal to the angle of reflection. So if this is the quickest way to the bonfire, if this angle is equal to this angle. Why I think that in reality, if you're talking about a person with a bucket of water, probably the quickest way would be like this. Can anybody think of a reason why? Where's the chat? Yes, Ben, for what reason? Oh, yes, the added weight of the water. Yes, it will take you longer to run with a heavy bucket, so you want to minimize the time. You want to run longer with an empty bucket and run a shorter time with a full bucket. But assuming that you run at the same pace, this is the quickest path. Quickest if theta I equals theta R, assuming a constant speed. Okay, perfect. And then let's look at refraction of light, which is a very similar story. If you take a boundary between air and let's say water, so this is view from the top. This is the bird's eye view. Yes, bird's eye view. Bird's eye view. I hope everybody understood that. Boundary between air and water, and if light hits the boundary, it refracts. So light hits the boundary and it refracts. You know that. And we know the Snell's law that says that the angle of incidence, the angle of refraction, so sine the angle of incidence divided by sine the angle of refraction is equal to the refractive index of water divided by the refractive index of air. But the refractive index of air is very close to 1. It's approximately 1. It's 1.009 or something. It's really close. So this is approximately NW. So sometimes you will see sine of the angle of incidence, sine of the angle of refraction is equal to N. You would sometimes see it written like this. What it actually is, it's this law, just with the assumption that N air is 1. So we'll scrap that. Let's write it properly. And it doesn't have to be incidence and refraction. We'll say it's theta 1, theta 2, N2, N1. Another way of writing it is N1 sine theta 1 equals N2 sine theta 2, where N1 and N2, yes. Then it turns out that if light goes from A to B, then this is the quickest path. Path from A to B is quickest. If so N1 sine theta 1 equals N2 sine theta 2. And I really enjoy this analogy. So let's say you are sunbathing on you're sunbathing and on a beach. Okay, Let's use you. And this is a beach. And this is the sea. Okay, so there's the sea. This is bird's eye view. Yeah, so this is a view from the top. And in the water, there is somebody, potentially the person of your dreams, crying for help. They need help for whatever reason. Perhaps they are drowning. And you are the only person and you need to help them. So how do you run? Do you run directly to the water and then swim? Or you just take the shortest path? Or perhaps you run to this point and then swim from here? Well, it turns out, well, if you're like me and you run faster than you swim, which probably is true for most people, the quickest way to help the distressed person is if this angle, θ1 and θ2, if quickest if θ1 sine θ1 divided by sine θ2 is equal to speed of running divided by the speed of swimming. Which is the same as to say this is the refractive index of water over the refractive index of the beach. Okay, did you learn something new in the last 10-15 minutes? Yes or no? Yes, good. That's good. That's great to hear. So yeah, light does take the quickest path, and it's fascinating because, well, you can sort of decide, you can do a rough calculation in your head. It could be intuitive, but light does naturally, as if there's some sort of like intelligence, or of course there's not. It also comes down to the minimization of energy. I want to say minimization of energy. Yeah. Right. Okay, so let's do some maths. So we need to prove that the path taken by light from point S to point M. So point S is a light source. It's a light source. And it's underwater. And M is your eye. And light takes the path SBM. And you need to prove that the time is minimal if the Snell's law applies. Show that the light takes the quickest path between the source S and the eye of the observer when n1 sine θ1 is equal to sine θ0. In other words, yeah, Snell's law. Because n0 is n of air, which is 1. So that's why you can see that n0 is omitted here. So we need to work out what n1 is. So n1 is the refractive index. So it's the speed of light in air divided by the speed of light in water. This is an important thing. So we can say that's V0 divided by V1, or simply the speed of light divided by the speed of light in water, which is different. Okay. So now we need to find the time to travel. From S to B. So that we have a time SB. Time SB. And it's equal to the distance SB divided by the speed, so V1. And we know that SB is, from trigonometry, is x over sine theta, sine phi 1. So x over V1 sine phi 1. Secondly, do we know everything? Yes. So x is our variable. X is the variable that's going to change. Okay. Now time to travel BM is equal to oh no, sorry. I don't want to do that. Let's do it slightly differently. Time to travel SB is the distance SB, and the distance SB is x squared plus h squared. It's BS, okay? SB divided by the V1. And time BM, so that's going to be time to travel from B to M. Well, it's the distance BM. So this is H. We kind of need, well, this distance BM is H. Okay, let's draw this. Let's draw a triangle. Let's call this Y. So tan, oh, we don't need tan, sorry, we need cos. Cos theta phi 1, cos phi 0 is H divided by BM. In other words, BM is H over cos theta phi 0. Sorry. Okay, so that's H over cos phi 0. And multiplied by c, the speed of light. So the total time no, that doesn't work. Doesn't work like this, because if you change x, phi 0 is going to be a variable, so you can't have phi 0 as a variable. Just let me give me a sec. Oh. Right, so that is Now this would lead us to have a new variable here. So yeah, it's inescapable. It's something I wanted to avoid. We'll have to do it in terms of, oh, here it is, L, of course. Silly me. This is L minus X. This is L minus X. Apologies. Minutes of madness here. So we have BM. The time to travel from B to M is going to be square root of h squared plus L minus X squared over C. Okay. So the total time, T, is equal to square root of x squared plus h2 over v1 plus square root of h squared minus L minus X squared over C. Second. Yeah. Okay, so this is the time. How do we find the minimal time? Can somebody help me with that? Where's the chat? I lost the chat again. Differentiate with respect to what? Yes, beautiful. Thank you. So we differentiate with respect to x, of course, because x is our variable. We're choosing where the light will hit the boundary. That is, we're choosing x. X is our variable. We differentiate with respect to x. So dt dx is equal to, so we use the chain rule here. So that's going to be 2x multiplied by, so it's to the power half, so it's minus a half, so 2 v1 square root x squared plus h squared plus, so here we have, so we need to differentiate that, so it's going to be minus x squared, so minus 2 x minus 2x minus, this is going to be minus plus 2l plus 2l. Oh yes, it is plus. Apologies. So there's no minus, so L plus X. Thank you. But that means it's going to be minus L. It's going to be minus L to X minus 2L over 2 square root h squared plus L minus X squared C. Okay, so the 2's cancel. Okay, and we have x over v1 square root of x squared plus h squared plus x minus L divided by x h squared plus l minus x squared times c. I'll put c here. And this has to equal to 0. In other words, x over v1 square root x squared plus h squared has to equal to L minus x. So I'm changing L and x around, L minus x over c square root of h squared plus L minus x squared. And x divided by x, that's the important bit. X divided by square root, so x divided by bs, which is x divided by square root of x squared plus h squared, is actually sine phi 1. So this is sine phi 1. And this, similarly, this is sine phi 1, and this is sine phi 0. So we are left with sine phi 1 divided by v1 equal to sine phi 0 divided by c. And we remember that v1, c over v1 is n1. So from here, we can say that v1 is c divided by n1. We plug that in. So c divided by n1 sine phi 1 equals sine phi 0 divided by c. Bam. n1 sine phi 1 is equal to sine phi 0. A beautiful result. Oh, I mean, I think it is. I think it's a beautiful result because this is just, yeah, showing that the Snell's law leads to the quickest path. We didn't prove the Snell's law or anything like that, but we have shown the Fermat's principle of the silent T, Fermat. So Fermat. Okay. Any questions? Any questions? Anything you weren't sure about? Okay. The rest of the problems are easier. Okay, so don't worry. The remaining problems will be, well, problem 3 is slightly trickier, but nothing serious. A desk lamp that can be considered a point source of light is placed 60 centimeters above the desk. A triangular mirror with sides 5, 6, and 7 is placed on the desk. The lamp is 1.8 meters from the ceiling. Find the position of the image of the lamp filament. The mirror forms a bright spot on the ceiling. Find the shape and dimensions of that spot. Okay, so we start by drawing. So there is a table. And there's a lamp on the desk. So let's say there is a lamp. Lamp L. They say it's 60 centimeters above the desk. Oh. "60 centimeters." And there's a mirror on the desk. There's a mirror on the desk. The lamp is 1.8 meters from the ceiling. So there's a ceiling, and it is 1.8 meters. The ceiling. And find the position of the image of the lamp filament. That's an interesting thing. So like you can use your phone as a mirror, right? So most phones are pretty good at reflecting stuff. So you can see reflections in a mirror. So you can see the sky reflected in my phone. And yes. So one thing you've learned about mirrors, well, one thing you should have learned about mirrors is that the image in a mirror is always the same size as the object itself. Okay. Now, look at that. Do you see a house reflected in my phone? How come like doesn't that contradict? So what I'm trying to say is the image in a plane mirror is always the same size as the object. Object and image are the same size in a plane mirror. How come this image fits on my phone screen? My question to you is the image of this house the same size as the house? Okay, so please tell me, is the image of the house that you see in my phone the same size as the house? No. But that contradicts what you know about mirrors. No, but it is the same size as it would be if it was the same distance away as the light travels, only in that direction. That is not exactly correct, although it's closer. It's close. You're getting close to the truth. Okay, the first thing that you need to know: images in a mirror. Image in a mirror. In a plane mirror, of course. Plane mirror. A. First, it's the same size as object. 2, it is the same distance from mirror as the object. That's an important thing. It's the same distance. So the distance from the house to the mirror is exactly the same as the distance from the mirror to the image of the house. In other words, you're standing in front of a mirror. This is you. And this is a mirror. Your image is here. Well, let's make it a mirror image. It's always the same size and always the same distance. So if this is you, this is your image. It's always the same size and always the same distance. So what's the deal with the house? Well, it's obviously true for the house as well. It's just the house is so far away and the mirror is small. It doesn't change anything. You're viewing the house, which is, okay, let me draw like a humongous diagram. Go here. And this is the mirror. This is a house. I think I got the scale about right of you, the mirror, and the house. But the house is so far away. And the image of that house in the mirror is exactly the same distance from the mirror. And this is you holding a mirror, and you're viewing that image inside the mirror. You're viewing that image inside the mirror. You're viewing it like this. Through the mirror. So pretty much the whole house fits in the mirror. Because that's your angle of sight. This is the angle at which you are seeing. So let's just adjust it slightly. Okay, I'll take a slightly bigger mirror, just for it to make sense. Do you understand the diagram? So light travels from the house. Light travels from the house, bounces off the mirror into your eyes. So this is how light travels. Light travels like this, bam, and then bounces into your eyes, bang, and bounces into your eyes. But what you see in you see the image of the house, image of house, because the image is so far away. It's like looking at the house through, I don't know, through like making a circle. I can see the whole house. The house has to be the same size as my fist, because it fits in my fist. You don't say that. Therefore, the image of the house, which you see in a mirror, is exactly the same size as the house. But because you're so much closer to the mirror than the house, that's why you can see the whole house in the mirror. Okay? Have I convinced you? Have I convinced you that the image and the object are always the same size? If it is a plane mirror, of course, because if the mirror is curved, and we'll do curved mirrors next time, then it's no longer the case. But we're talking about flat plane mirrors. Okay, so here we have a lamp. Now, the image of a lamp is exactly the same size and exactly the same distance from the mirror. But the problem is, well, the image is not here, because no matter the size of the mirror doesn't matter. It's the plane of the mirror that matters. So the image of the lamp would be the same as if, well, if the mirror was here, the image would be here. But if the mirror was here, that doesn't change the position of the image. Because if you're looking from here, for example, if your eye is here, you would see light bouncing off the mirror and into your eye as if the light is coming from here. So moving the mirror along the table does not change the position of the image of the lamp. Therefore, you would have the image of the lamp is here. Even if the mirror is elsewhere on the table, the image is here. Image of lamp is the same size and the same distance. So this is 60 centimeters. 60 centimeters. So now it looks as if the light is coming from the image, because what mirrors do, they trick you. They trick you into thinking light is coming from behind the wall. If you shine light onto a mirror, it looks like the light is not coming from where it's actually coming. It looks like it's coming from the wall. It looks like behind the wall there's somebody else standing, which looks exactly like you, slightly more sophisticated, slightly more left-handed if you're right-handed, and the other way around. And the light is coming from there, and the light is coming from the image, and it passes through the mirror, and it forms a triangular bright spot on the ceiling, which is exactly the shape as the mirror. Sorry, I meant to draw it the other way around, but it doesn't matter. So you have bam, bam. It's a triangular bright spot. Triangular bright spot. And then you use the fact that these two triangular pyramids are similar. Use similarity of shapes, of 3D shapes, to work out the dimensions. So because this is 10 centimeters, 60 centimeters, and the whole height is 180 plus 60 plus 60, so that's 300 centimeters. So the large pyramid, triangular pyramid, is an enlargement by scale factor of 5. The larger pyramid is an enlargement of the smaller one. Smaller scale factor to equals 5. Hence, the bright spot has a shape of a triangle. The bright spot the shape of a triangle with sides 25 centimeters by 30 centimeters by 7 by 35 centimeters. That's B. And A, image of the lamp is 60 centimeters below the desk, just directly below the lamp. Okay. The next problem, and I think it's one of the problems from the assignment. When looking down into a swimming pool, the pool seems shallower than it actually is. Find the actual depth of the pool, and the perceived depth is 2 meters. So not much information. And indeed, if you look at a picture, it seems like the pool is like really shallow. Look at that. Look at that depth. It seems like you can barely. Oh, it definitely seems like if you jump into this pool, you'll break your legs. But it's not the case. It's actually a standard depth. How would you measure perceived depth? Well, you compare it to a meter stick, basically. So you take the photograph, you place a meter stick here next to the swimming pool, and then you measure this distance. You measure this in centimeters, and then measure this in centimeters, the length of the image in centimeters, and compare, and then you can work out the perceived depth. So you take a photo of something you know the length of and compare the pictures. Does that make sense? Okay. So this is the perceived depth. So it looks like what, 30 centimeters perhaps, and comparing it to the size of this chair. So I'm assuming this chair would be about 35-40 centimeters, and it's about the same. So it looks like the depth of the pool is approximately the same size as this chair, which is about 40, let's say 40 centimeters in this particular case. This is what we mean by when we say perceived depth. Okay, find the actual depth of the pool if the perceived depth is 2 meters. So we'll need a diagram. So let's say we have, whenever you have a question on refraction, the first thing you do is a diagram. So you have the edge of the swimming pool. And this is the bottom of the pool. Okay. So let's say you are standing somewhere here. This is your eye. And light is traveling from point S. We usually put S as the source of light. And light travels like this. And then refracts into your eye. Now, because light refracts, but your brain has been taught from early childhood that light travels in straight lines. Okay, this is what you've been taught. Not necessarily like taught. No, but this is a thing you automatically assume. Light travels in straight lines. If you see something straight ahead, you assume it's there. Okay. Whereas in reality, things could be refraction. In reality, it could be like this. Refraction tricks your brain. So you see the body of a person here. You assume that light travels in a straight line. So you think that the body is there. Whereas in fact, and I think with a very high degree of certainty, we can say that the body is actually here. Okay. Experience tells me that the body is usually underneath the head. Okay. So yes. So this happens because light doesn't travel. Light does not travel in a straight line here. So you have the swimming pool, and this is you. This is headless Nick. This is the person in the pool. This is the person's body. This is the person's head. You see the head through the air, so you see the light coming from the head directly. But the light from the body is going through the water first. It's going through the water and then comes out like this, refracts. So you think the light from the body is actually coming from here. That's why you see the image of the body, image of body. And the image of head is where it should be. It's in the same place as the head, but the image of the human body is in a different place. This is why it's confusing. So your brain tells you light travels in a straight line. So if you see something in front of you, that means something is in front of you. That's what I'm trying to say. That's why people bump into mirrors quite often, because they think that there's a corridor, and they walk into a mirror. So the light travels from point S, which is the source of light. So the source of light is just the bottom of the swimming pool. It doesn't have to be a literally source of light. Any point is a source of light because it has light falling onto it. Light is reflected. Therefore, something becomes a source of light. So I can say that my favorite cup is a source of light because light reflects off it. Okay. That means we have, yes, okay, I've been talking for a lot. Now, our brain tells us the light is not coming from here, but the light is coming from here. S1. We need a second ray of light, and the second ray of light just goes straight up. So we use this as the reference point. So the second ray of light just goes straight up, and from here it would also go straight up. So this is the position of the image. We know that this is theta. Let's call it theta 1. Let's call this theta 0. Theta 0. And we know that this is 2 meters. And we need h, the actual depth of the swimming pool. H. So let's take this distance as x and write some trig stuff. So this angle is theta 1. So sine theta 1, sorry, not sine, is it tan? Yeah, tan. Tan theta 1 is equal to x over 2. And tan theta 0 is x over h. And we can x over h, we can say that tan theta 1 divided by tan theta 2 is equal to x over 2 x h, x cancels, so it's h over 2. On the other hand, for small angles of theta, if theta is small, tan theta is approximately equal to sine theta. So we can use that. There's going to be sine, so it's approximately equal to sine theta 1 divided by sine theta 2, which is equal to h over 2. And sine theta 1 over sine theta 2, we already know, is the refractive index of water. The refractive index of water is about 1.33. So h is equal to the actual depth is 2 times n, which is 2 times 1.33, which is 2.66 meters. So you see the swimming pool is 2 meters, but the actual depth is 2.66 meters. But this is only when you view at a small angle of theta. This is when you are looking directly down into the swimming pool. When looking down into a swimming pool. This does not apply to the diagram that I have drawn, because here the angle is really, really big. And you cannot use the sine. It just, the maths becomes way more complicated. So you would need to know the angle at which you're viewing. This is a simplified expression where so this approximation only works with small angles. I hope that makes sense. This angle theta is a small angle. So you're looking down into the point, and that's why the bigger the angle, the less the depth. So it will change with the angle of view. Right. I hope I haven't confused anyone. Problem 4 we'll skip because it's lenses. It's for the next assignment. So hope you're excited for lenses. Problem 5. I really like this one. What is the angle of incidence if the refracted ray is perpendicular to the reflected ray? Let's play around with some angles. So bet refraction. The angle of incidence of the refracted ray is perpendicular to the refracted ray. So what does that mean? What does that mean? Let's have a look. So you have a ray of light, and the angle between the refracted ray and the reflected ray is 90 degrees. So what they're saying is that this angle is 90 degrees. They're asking us to find theta. Okay, so they give us the speed of light in glass, and that means we can find the refractive index. The refractive index of glass is the speed of light in vacuum divided by speed of light in glass, which is 3 times 10 to the 8 divided by 2 times 10 to the 8, which gives us 1.5. The refractive index of glass is 1.5. So we know that this angle is, we'll call this theta 1, theta 2. We know that sine theta 1 divided by sine theta 2, theta 2 is equal to n. Okay. What else can we do here? This angle, so this is theta. This would be 90 minus theta 2. And this would be theta 2. Therefore, this would be 90 minus theta 2. Yes. Okay. But we know from the law of reflection that theta 1 has to equal to 90 minus theta 2. because the angle of incidence has to equal to the angle of reflection. So these have to be equal. So in other words, theta 2, that means theta 2 is equal to 90 minus theta 1. When we plug that in, it's going to be sine theta 1 divided by sine 90 minus theta 1. And what is sine 90 minus theta 1? Sine 90 minus theta 1. Can somebody help me? Cos theta, of course. So it's going to be sine theta 1 divided by cos theta 1 equals n. So tan theta 1 is equal to n. Theta 1 is arctan of n, which is arctan 1.5, which is approximately 56 degrees, I think. Arctan 1.5 divided by 56.3 degrees. 6.3 degrees. Okay. Now, this is not a coincidence. This angle has a meaning. It's called the Brewster angle. So when this angle is known as the Brewster angle. One is known as the Brewster angle. This will be studied in year 13. In short, I will say that it is the angle at which the reflected light is polarized. This angle reflected light is polarized. And it has very interesting applications. Very interesting applications. For example, we can measure the polarization of the reflected light. We'll talk about polarization in year 13, so don't worry if you don't understand what it is. But the thing is, this angle, you can measure this angle without having a refracted ray. In other words, you can find the refractive index of non-transparent materials. So if you have a non-transparent material, you would have, can I get a, so if you have a non-transparent material, basically you don't have the refracted ray, you can't measure it. So this disappears. And but you can measure the angle of polarized. So let's say you have a material which is non-transparent. you measure this angle, theta, and you measure the polarization of this ray. And once it is fully polarized, you can use a polarizer for that. Use a polarizer for that. So at some angle, so this is a non-transparent material. Non-transparent. At some angle, theta, the reflected light is polarized. It's polarized. And this angle is known as the Brewster angle. And because we know that tan theta is equal to n, we can find the refractive index of a non-transparent material. Now, if you ask me why we need it, I don't remember, but it must be, it certainly has applications. It's just I don't remember which ones exactly. So this is thus you can find the refractive index of a non-transparent. If I have misspelled transparent, sorry, end of the day. Transparent, the single R. Transparent. Sorry. Transparent. Okay, that is good. That's problem 5. And then I wanted to talk you through a little bit about the questions from the assignment. I won't do them, but I will give you some hints. So problem 9, this is a PAT question. A monochromatic beam of light travels through air refractive index and strikes a liquid refractive index n. There's a mirror. So there's a mirror at the bottom of the tank. Mirror, and light strikes it and refracts into the glass, and then reflects at some angle, and turns out that this angle is critical. Critical angle, as you should know, is when there's no refracted ray. So basically, the light is refracted along the boundary. Therefore, this is 90 degrees. So you need to find theta, and here you just apply the laws that you know. This is a more like a question on geometry. Beyond a certain value of theta, the light no longer leaves the tank after the first reflection of the mirror. So you can see that this so the critical angle. So you have, well, let's have a look at the critical angle, by the way. We haven't discussed it. So let's make this water, let's make this air. And you can see that when light travels from water to air, it sometimes doesn't refract. So it refracts and reflects, refracts and reflects, refracts and reflects, and at some point, the angle of refraction becomes 90 degrees. And at this point, there's no light leaving the water. Okay. And if you measure the intensity is 100%, 100%. 100%. And you can see that here it's 30%, 100%, 69%, 69% and 30%. And the bigger the angle, the bigger the percentage. So you can see, like here, 96% of the energy goes through. At this angle, 81% of the energy goes through. And the bigger the angle, the less energy goes through. And by the time we reach almost critical angle, this percentage drops to 0. So it's not that the light is actually refracted along the boundary. No, it's more like the 100% of the energy goes into the reflected ray. So you can see it disappears, like here, it's 100%. So 100% is reflected, 0% refracted. So when you see diagrams where light is refracted along the boundary, it doesn't actually happen. You have reflection, and we say the refracted ray goes along the boundary. It doesn't really happen. What actually happens is it just reflects back like this. It will keep bouncing forever. The question is, what is the angle theta so that it does that on the first bounce? On the first bounce, if this angle is theta, if this is well, basically what happens when light comes in, this is going to be theta, this is theta 1, this is going to be theta 1 plus 2 phi. That's what's going on. So this angle increases by 2 phi because of the reflection, because of the slanted mirror, and then it doesn't leave. Okay, I don't want to do the maths here. I want you to figure it out. Do you have any questions about this problem? Okay. Problem 10. What is the minimum radius of curvature R of an optical fiber with diameter L and refractive index of n such that the parallel beam of light entering one end and aligned with the normal stays within the fiber? Okay. So let's have a look. Well, if a ray hits like this, it's almost certain that it will be reflected back into the fiber, because the angle of incidence is close to 90 degrees here. But let's look at the other extreme point. The other extreme point is here. Light coming in here. Goes straight through the glass, and then you can see that this angle is far from 90. So this angle has to be critical. This angle has to be subcritical. The theta needs to be less than the critical. And the critical is arc sine 1 over n. So you need to use a little bit of geometry here just to figure that out. And the theta depends on r, of course, because the smaller the radius, the more it is bent, and the bigger the angle is going to be. Okay. And optical fibers should not be bent because, well, you don't want an optical fiber to, you don't want the light to escape from an optical fiber. finally, this question, the problem 14. An experimental setup consists of 2 deep tanks, each of width L, separated by a thin transparent membrane as shown. The left tank is filled with transparent liquid. The right tank is with a transparent liquid with refractive index of N2. The membrane has a refractive index N1. Assume that the refractive index of air is 1. A gold ring is dropped to the right pool with a refractive index of N2 near the membrane and drops straight down. An observer at height h above the left edge of the experimental center watches the ring drop. The dashed line indicates the path of the light ray from the ring to observer. At a certain depth, the ring will appear to the observer to stop descending. At what apparent depth does this happen? Okay. So basically, what's going on here? The ring, the light from the ring so this is the ring and the membrane. And so the light travels from the ring to the membrane, refracts and refracts again. Now the ring stops descending when this line is exactly vertical. This line, when this line is vertical, well, it will stop descending. In other words, if we draw, this is the angle of angle 3, this is angle 2, this is theta, this is 90 minus theta 2, and this is theta 1. And then you just write down the Snell's law with theta equals to 3. Snell's law, so sine. I won't do it because this I've pretty much solved the problem. When this is so theta's 3 has to be 90 degrees. 90 degrees. And you apply the Snell's law twice. Once for this boundary and once for this boundary. So this is N1, N2, and this is N0, which is 1. Okay. So I hope that makes sense. Okay. I hope this was useful. I hope you enjoyed it. So I'll see you next week. Next week we'll do some equations. If you have any questions? Yeah. All right, you're welcome. Welcome. See you then.